So this video, I just have two more practice problems that work with protecting groups. So this first one, it looks like it has 5 steps. You kind of say it's 6 if you wanted to, but let's just get right into it. So why don't you guys go ahead and try to attempt the problems 1 through 6 or 1 through 5, however you're looking at it, and we can work on it after. So in part A, we're given sodium hydride, THF, in cold conditions. Cold conditions just controls how often the sodium hydride is going to deprotonate something. To that end, sodium hydride is only a source of base and will never act as a nucleophile. So it's going to look for the most acidic thing, that's going to be the alcohol in this case, and it will deprotonate that alcohol completely. So complete deprotonation of the alcohol. That was a kind of bad epoxide. We'll leave you with this O-. And so part 1b introduces benzyl bromide. So benzyl bromide with this anion on our oxygen will let us do an SN2 here. So performing SN2 gives us this thing down here. And this group OBN, it's kind of nice to us because that's at least our first protecting group that we'll see being used here. We know it's easily reversible with reduction with hydrogen with palladium on carbon. And if we look ahead, we can see that in step 4, we actually do see those conditions. So it's a good bet that we're on the right track so far. Going on to step 2, methanol with catalytic CSA. CSA, you can kind of treat it like it's sulfuric acid. It's, I believe, a slightly stronger form of acid than sulfuric acid. But for us, we're just going to treat it like it's an H+. So it's just going to be protonating things. In this case, it's going to protonate the epoxide. When you protonate the epoxide, now the methanol is going to be more likely to do a nucleophilic attack. Now we just have to figure out on which side is it going to attack. Is it going to attack that carbon, or is it going to attack this carbon? We can answer this if we drew, real quick, I'm going to do it up here in the corner. If we drew a chair, okay, let's go ahead. We're going to put the OBN on an equatorial position because that'll give us the least steric interactions, which is good. I'm going to put the epoxide pointing down because they're both on a dash. So they're pointing down right here. Okay, so recognizing where the H's are, that's the important part. And in this case, we have an H if the benzyl, the OBN group, is on equatorial plane, then the H is on an axial plane. Okay, so over here to the right of our epoxide, the epoxide is going to be pointed down, or we can also think about it if this H is axial up, the next position down will be axial down, axial up, axial down. So you'll have an H that's axial down and an H that is axial, or that is equatorial up, excuse me. And so the thing that we care about is getting to this carbon and this carbon from the top. And so you have to ask, what's easier to do? Is it easier to approach the epoxide in this way where the brown arrow is pointing when there's an H that is pointed up in your face, or there's an H that is pointed out to the side? And the answer is, obviously, when it's out to the side, there's going to be less steric interactions, so you're going to want to attack it at that side. So that's a long story for explaining that in the end, our product is just going to look like what I'm about to draw. There's that methyl. And our alcohol. So the alcohol stayed on a wedge, and the methyl group the alcohol stayed on a dash, and the methyl group went on a wedge. And that just has to do with backside attack. So number 3, we're given TBSCl. From the last video, we learned that TBSCl is just TBD or TBDMSCl, which is just a really big, bulky protecting group for us. So if we're to use that here, let's go ahead and protect the only alcohol that we have left. So protecting this alcohol, OTBS, just like that. Now, when we introduce some hydrogen with palladium on carbon, we mentioned that in step 1b, hydrogen with palladium on carbon will reduce that OBN group back to its alcohol. So at this point, this is what we have. So step 5, you're going to take, excuse me, I left out the OTBS. OTBS. So in step 5, PCC, it's selective oxidizer. It will oxidize our alcohol here into a ketone. So getting rid of stereochemistry, and there's your ketone, your methyl group, and your OTBS. Okay, in this problem, it's a little bit different style. Instead of giving you all the reagents to get to a final product, we're kind of doing a little bit of retrosynthetic analysis with filling in the blanks of how we actually got to our product. So again, it's going to have to do with protecting groups. So go ahead and give it a try real quick, and then we can work out the solution together. So with this problem, the only thing that we're noticeably changing right here is we're changing this carboxylic acid into this 3-carbon double bond system over here. So how do we do that? Well, ideas is that you could probably do some sort of esterification and then reduce whatever that ester is all the way down until you can get rid of, you can either get down to the alcohol and get down to the hydrocarbon, and then either do an elimination or do some sort of radical chemistry. But in this case, I think elimination might be easiest. So let's go that route. But in order to get there, we should notice that these alcohols right here are going to be an issue for us. And not even those alcohols, not only those alcohols, but also this carbonyl, right? Because under acidic conditions and basic conditions, these two groups in green will be an issue. So let's protect them. And the first way to protect the alcohols that I think would be easiest, so if we said step 1, we're going to introduce some acetone and then also some H+. So why are we doing this? Well, when we introduce some acetone and H+, we will get right here. We end up with this. So it's kind of the same thing as doing ethylene glycol. It's just our ethylene glycol is already in our molecule. So for the second thing we should do, we should go and protect that carbonyl. So we can selectively protect the carbonyl without affecting the carboxylic acid with using ethylene glycol. So ethylene glycol will not affect carboxylic acids, but they will affect ketones. So here's your ethylene glycol. And we have to run this with some acid. And that will get us everything we already have, plus this group protected. Okay, so the third thing we should do, if you're thinking esterification, that's the route I was going to go. So let's esterify. So I think the easiest way, and it doesn't matter what ester we get right here, but the easiest way to esterify carboxylic acid is probably just use diazomethane. So diazo. There's the methane part, and this is the diazo. We know diazomethane will just make that a methyl ester, which is great for us. So the methyl ester. So now the fourth thing we'd probably want to suggest to do is to actually get in those methyl groups that we want. So to put in those methyl groups, let's first use either a Grignard or an alkylithium reagent. So I'm going to suggest a Grignard, but if you want to do an alkylithium, that's fine. So methyl magnesium bromide. And I guess I could say, I'm going to say like 2 equivalents, 2 EQ. The purpose of that is to let it attack the ester, kick out the methoxide group, and then attack it again. So, and let me actually do this since we're running out of space. Let's call this 4A, and 4B, since we know Grignards are always followed up by acid. That should be trivial at this point. So the products of 4A and 4B should look like this. Okay, so now that we have parts 4A and 4B answered, we should now just the home stretch is to get our protecting groups changed back into the alcohol and the carbonyl, and then also perform an elimination. So we knew that was kind of the route we were going to go. So I'm going to put step 5 up in this left corner right there because we're kind of out of space at this point. But if we introduce some acid, so I'm going to suggest tosylic acid. You could probably use sulfuric acid and water just fine. Using water and sulfuric acid is the generic way to reverse protecting groups, especially these ethylene glycol protecting groups. But when we introduce the acid, you'll protonate this alcohol, and then the conjugate base will pull off this proton that'll allow you to do an elimination reaction, and that'll get you to the product, and it'll also change back these protecting groups into the carbonyl and to the diol. I should also note that I kind of dropped it out, but there are dashes all right here. I shouldn't have left that out, but they are still there, just like that. So let's draw the product from using tosylic acid. So here I have the final answer underneath step 5, which is just our product that's over here in pink on the right. I think we ended up using, what's that, about six steps to get to our final answer. It's not bad considering that we had to protect 2 different groups and then reverse 2 different groups and also change a functional group. So 6 steps, all things considered, isn't that bad at all. So if you ended up having a 6-step synthesis, then even if it was different than this and you got to the same thing, that's probably a good suggestion. So that's it for this problem.